Okay, today we're looking at section 3.5, irrational numbers. So we've defined rational numbers in the previous section, the numbers that can be expressed as a fraction of two integers. Irrational numbers are numbers that cannot be expressed as a fraction of two integers. Recall that rational numbers can be identified as those whose representations either terminated or had a repeating pattern at some point. So irrational numbers must be those whose decimal representations do not terminate or become a repeating pattern. One collection of irrational numbers is square roots of numbers that aren't perfect squares. Square roots of numbers that aren't perfect squares. X is the square root of the number a, denoted square root of a. If x squared equals a, the number a is the perfect square of the integer n. If a equals n squared, the rational number a divided by b is a perfect square if both a and b are perfect squares. One method of determining if an integer is a perfect square is to examine its prime factorizations. If in the factorization all the prime factors are raised to even powers, the integer is a perfect square. Another method is attempting to factor an integer into integer squared. It is possible that you recognize a number as a perfect square, such as 4 or 9. Or if you have a calculator at hand, you can use the calculator to determine if the square root of the integer is an integer. So which of the following are perfect squares? Okay, well, let's try the factoring here. So we have 2, which leaves me 18, and we have 2, which leaves me 9, which is 3 and 3. So I have 2 squared times 3 squared, so 6 squared. It is a perfect square. Looking at 27, I have 3 times 9, which is 3 times 3, not a perfect square. Here I have 9, which is 3 times 3. I have 49, which is 4 times 9. So it is, and it's 3 over 7, or which is 7 times 7. Here I have 12 over 221. 12 is not, so not. Another collection of irrational numbers is based on the special number pi, which is denoted by the Greek letter pi. This is the ratio of the circumference to the diameter of a circle. Any multiple or power of pi is an irrational number. Any number expressed as a rational number multiplied by an irrational number is an irrational number also. When an irrational number takes that form, we call it a rational number, or we call the rational number the rational part and the irrational number the irrational part. It should be noted that a rational number plus, minus, multiplied by, or divided by any irrational number is an irrational number. So, which of the following numbers are irrational? Can I take the square root of 225? In this case, we'll just use our calculator. Square root of 225 is 15. So this is rational. The cube root of 5, what times itself twice gives you 5? Not a normal number, so this one is irrational. The square root of 80, that's not a perfect square, so that's irrational. And of course, anything with pi in it is irrational as well. To simplify a square root means that we rewrite the square root as a rational number times the square root of a number that has no perfect square factors. Number inside the square root symbol is referred to as the radicand. So for any two numbers, a and b, the square root of A times B is equal to the square root of A times the square root of B. So simplify the irrational number 550. Express it in lowest terms. Identify the rational and irrational parts. So let's see. Let's look at 550. Well, that's 5 times 110, which is 5 times 21, which is 3 times 7. So I do have a 5 squared. So the square root of 550 is the square root of 25 times the square root of 21, which is 5 times the square root of 21. 5 is rational. Square root of 21 is the irrational part. Okay, so let's simplify the square root of 733. 2 don't, 3 don't, 4 don't, 5 don't, 6 don't, 7 don't, 8, 9, 10. Nope, 7, 13. Looks like we may be done here. 17, 19, 23. Trying to find a factor. Looks like it's going to be a prime number. One more, I think. 29. Yep. So this is a prime number. Our 733 is prime. So this reduces down to simply the same thing. And it is the irrational part because it is an irrational number. Okay, what about 1815? Let's see if we can break this down and see what happens. So I can see there's a 3, gives me 605, which has a 5. Which gives me 121. 5 times 121, which is 11 times 11. So this is the square root of 1815 equals the square root of 15 times the square root of 121. Square root of 121 is 11, so I have 11 times the square root of 15. And the 11 is the rational part. Square root of 15 is the irrational part. Okay. So now we're going to look at adding and subtracting irrational numbers. Just like any other number we've worked with, irrational numbers can be added or subtracted. When working with a calculator, enter the operations and a decimal representation will be given. However, there are times when two irrational numbers may be added or subtracted without the calculator. This can happen only when the irrational parts of the irrational numbers are the same. Kind of like when we're adding fractions, the denominators have to be the same. If we're adding and subtracting irrational numbers, the irrational portion has to be the same. To add or subtract two irrational numbers, they have to have the same irrational part. Add or subtract the rational parts of the numbers, then multiply that by the common irrational part. So let our first irrational number be a times x, where a is the rational part, x the irrational part. Let the other irrational number be b times x, where b is the rational and x is the irrational part. Then a times x plus or minus b times x is simply a plus or minus b times x. So what do we have here? We have 41 times the square root of 15 minus 23 times the square root of 15. 41 minus 23 is 18, and we just keep our square root of 15. That's simple. Okay, now I have addition, not subtraction. Add. So I have 4.15 plus 3.25 pi. 4.1 plus 3.2 is 7.3 pi. That's simple. If possible, subtract the following irrational numbers without using the calculator. If it's not possible, state why. Well, let's look at this. The square root of 45. That is the square root of 9 times the square root of 5, which is 3 times the square root of 5. So now I have 2.1 times 3 times the square root of 5 minus 3.7 times the square root of 5. So now I multiply my 2.1 times 3. I get 6.3 times the square root of 5 minus 3.7 times the square root of 5. And that gives me 2.6 times the square root of 5. Okay, multiplying and dividing irrational numbers. Well, for any two positive numbers, a and b, the square root of a times the square root of b is equal to the square root of a times b. And for any two positive numbers, a and b, with b not equal to 0, square root of a divided by the square root of b is equal to the square root of a over the square root of b, or the square root of a over b. So to multiply or divide rational numbers, or irrational numbers, with similar irrational parts, do the following. Multiply or divide the rational parts. Necessary, reduce the result of step 1 to lowest terms. This becomes the rational part of the answer. Multiply or divide the irrational parts. If necessary, reduce the results from step 3 to lowest term. This becomes the irrational part. So I'm looking at 84 times the square root of 132 divided by 14 times the square root of 11. So this is simply 84 times the square root of 132 divided by 14 times the square root of 11, which is 84 divided by 14 times the square root of 132 over the square root of 11, which is this is 6. This is square root of 132 over 11. Did that factor down? I believe it does. And it does. So this is 6 times the square root of 12. 12 is 2 times 2 times 3. So this is 6. Yep, equals 6 times the square root of 4 times the square root of 3. Square root of 4 is 2. So we have square root of 3. 6 times 2 is 12 times the square root of 3. All right, dividing again. We have 57 over 25 times the square root of 792 over 2. 57 over 29 times the square root of 792 divided by 2, 396. Looking at the factors of 396, I see 2. It gives me 198, so I see another 2. That leaves me at 99. I see a 3. That leaves me with 33. I see another 3. That leaves me with 11. So I'm looking at 2 squared times 3 squared times 11. 4 times 9, 36. So this is 5725 times the square root of 36 times the square root of 11. This is 6. So I have 6 times 57 over 25 times the square root of 11. 6 times 57 equals, 6 times 57 equals 342. 342 over 25 times the square root of 11. Now we could do a mixed number, but I don't see the point at this time. Okay, multiplication. We're going to take 1.2 times 4.5, and then I have square root of 21 times the square root of 14. So we start out with this rational part here. 1.2 times 4.5 gives me 5.4. Now, square root of 21 is the square root of 7 times the square root of 3. And the square root of 14 is the square root of 7 times the square root of 2. So this will give me 7. 5.4 times 7 gives me 37.8. And I simply take 3 times 2 times the square root of 6. Here we have 38 pi over 2 pi, which is 38 over 2 times pi over pi. Well, 38 over 2 is 19. Pi over pi is 1. So our answer is simply 1. The next thing we talk about is rationalizing fractions with irrational denominators. Fractions often represent that some amount is being equally divided into some numbers or of parts. But to conceptualize a fraction in that manner, the denominator needs to be an integer. An irrational number in the denominator interferes with the interpretation of a fraction. Fractions that have denominators that are just the square root of an integer can be altered into fractions, or into fractions with integer denominators using a process called rationalizing the denominator. Process relies on the following property of square roots. Square root of a times the square root of a equals a. And the following property of fractions. A over b equals ac over bc for any non-zero number c. So using these two properties, when a fraction has a square root in the denominator, we can eliminate the square root to simply multiply the numerator and denominator by that square root from the denominator. So if we have a over the square root of b, we simply multiply a times the square root of b, and the square root of b times the square root of b. and we get a times the square root of b over b. So in our first case here, we have 24 over the square root of 15. Square root of 15 over square root of 15. Well, numerator is 24 times the square root of 15. Denominator then becomes 15. And that is that. Same thing here. We don't have to multiply by the 6. Just multiply by square root of 21. Square root of 21. So now I have 11 over 6 times 21. And this becomes, if we remember going back, 21 times 14 was, what did we end up with? 7 times the square root of 6. 7 times the square root of 6. And now to make this a little easier on us, we can factor out the 7, and I have 11 times the square root of 6 over 18. There are occasions when the denominator is irrational, but is the sum of two numbers where one or both involves square roots. This type of denominator can be rationalized. To rationalize such a denominator, we will multiply the numerator and denominator of the fraction by the conjugate of the denominator. The conjugate of a plus b is a minus b. So we say that a plus b and a minus b are conjugate numbers. So for any two numbers a and b, a squared minus b squared equals a minus b times a plus b. For any three numbers a, b, and c, a times b plus or minus c equals a times b plus or minus a times c. This is called the distributive property. So here, my numerator is 5 minus the square root of 13. So I want to multiply by the conjugate of that. So that's going to be 5 plus the square root of 13. And here too. Now on the top, it's simply 15 times 5, 75 plus 5 times the square root of 13. Now using this, a squared, well in this case, a equals 5. So a squared is 5 squared, which is 25. 25, and then we have minus b squared, which is b is the square root of 13, so b squared is 13, so minus 13. So we end up with 75 plus 5 times the square root of 13 over 12. Or traditionally, 75 over 12 plus 5 over 12 times the square root of 13. And that finishes up section 3.5.